We're talking about the next session, Inclusive AI for India and Beyond. And the speaker will present Google's work on inclusive AI, developing AI in a manner that brings its benefits to over 1 billion people in the context of India and the global south. Google's work on bilingual models to democratize information access in a diverse set of Indian languages, on healthcare in environments where we lack data in digital form to begin with, and on analysis of satellite imagery to help transform agriculture and improve the lives of farmers. And for the same, we'd like to invite Manish Gupta, Dr. Manish Gupta, Director, Google Research, who is the Director of Google Research India and a co-lead of a technology area in Google Research with teams across India, US, and Europe. Previously, Manish has led VideoCan, a video technology startup and a research center for Xerox and IBM in India. Please welcome Dr. Manish Gupta.
Good morning. Thank you. So I'll talk about, again, the work that we are doing on trying to bring the benefits of AI to billions of new people. So I'll talk about primarily 3 broad areas. How do I advance the slides? Should I? Okay. So I'll talk primarily about 3 areas. The first is democratizing access to information, then healthcare and agriculture. So starting with democratizing access to information, the primary motivation came from, again, just like the previous speaker in one of the sessions on digital public infrastructure, talked about bringing the benefits of technology, right, to people beyond those of us in the room, right, who are lucky enough to understand English. We have information at our fingertips. How do we provide the same kind of access to information for somebody, let's say the farmer's daughter in Chhattisgarh or a laborer's son in Assam? So before I talk about access to information in native languages, we have to look at even English that we speak and write in India is often a superset of formal English. And our team derived inspiration from this appetizer menu that they saw in a restaurant. And again, I mean, you might make fun of it and say, hey, why don't you spell it correctly? But if you really look at some of these entries like pineapple, appetizer, and so on, they actually do make sense. Because if you imagine the word in Hindi, and then you think about writing it in English, this is not an unreasonable way to spell, let's say, the word pineapple. And if you recognize that the sound z is missing in Hindi and the closest sound is j, then even this way of spelling appetizer makes sense. And of course, our motivation came from, we used to see, even in Google search queries, right, a lot of queries like this. And you don't want to just say, oh, I don't understand your query. You want to understand the user intent and serve the query. So that led to this work on Indophoneme, which was, again, understanding the phonetic origin, source of some of these ways of spelling things. And our team would basically look at these, apply some of these ideas to come up with, given, let's say, a word in English, come up with all of the different variants automatically of how, based on different kind of language influence and so on, you may end up pronouncing that word, and then how you might end up spelling that word. And again, this particular technique was used more recently in launching the spell correction feature within Google search, where it led to significant improvement in being able to understand Hindi queries. And of course, the other idea that the team is pursuing is from this, if you train a text, if you do a text to speech and create those various variants in how this word might be pronounced, you can now hopefully make your speech recognition systems much more robust to understanding different accents. Because as we all have experience with these automatic speech recognition systems, they work very well for people with kind of native English accent, let's say for an English recognition system, not so well for somebody like me with an Indian accent, and even much worse for somebody with a very thick regional accent. So then let me turn to how do we handle native languages. So today there's a lot of excitement about large language models, right? And let's just take a quick look at how these large language models are built. And for that, let me start with the first of these models called BERT that was built by Google researchers, and it was made available in 2018. The way BERT was built was basically that you started with all of this corpus of text on the web, sources like Wikipedia, and then what the team did was basically masked out roughly 15% of the words, and then trained this model, originally BERT, to then predict those masked out words. And since you had masked out those words, you already knew what those were, right? So this is known as self-supervised learning. And to me, this reminds me very much of this fill-in-the-blanks exercise that my English teacher used to give us when I was learning English, and then for any language that we learned. I also ended up learning Tamil in a school called Sardar Patel Vidyalaya right here in Delhi. And again, my Tamil teacher also used to give us this exercise. And while giving this exercise, they were testing two things, right? One is our ability to understand that language, and B, also ability to understand something about the world and reason about things in the world based on the context. So a similar thing happens when, let's say, this model, BERT, was trained to predict those missing words. It was forced to learn the nuances of the language, and it was forced to learn something, some representations about the world, which enabled it to predict those missing words. And once you build those models to predict those missing words, the researchers realized that not only were these models doing a good job of fill in the blanks, that now a whole bunch of natural language processing kind of tasks that you were asking them to do could be done by this model simply by doing a little bit of fine tuning. So tasks like sentiment analysis, you're trying to, let's say somebody posting things on social media, you're trying to see, is this person saying good things or bad things about my brand? Or things like summarization, which in fact the previous speaker talked about. How do you take all of this text, right? Some various interactions, let's say, that the service agent has had with the user and summarize those. Or answering questions. Given a piece of text, can you answer questions? So what these large language models, the first of these showed that starting with a single model, you could now fine-tune those models to solve all of those different tasks, starting with the same model. And fast forward to today, we have models like Palm, Palm 2, and of course GPT-3, GPT-4, which are being, again, utilized with as amazing starting points for you to be able to tackle a whole bunch of problems. So we wanted to, so if you look at any of these large language models, today their coverage of Indian languages is still relatively poor. So models like Palm, which Google has built, in fact do cover over 100 different languages of the world, including many Indian languages, but the overall representation is still not very good, which leads to a significant gap between these models' capabilities on languages like English and those for Indian languages. So our team then took on this challenge of how do we build multilingual models that understand all of the different Indian languages, and in particular, also phenomenon like code mixing, right? We often are in the habit of mixing multiple languages in the same sentence. एक ही sentence में अलग-अलग languages mix करना, that's something we often do a lot in India. So we built this model called Mural, which stands for Multilingual Representations for Indian Languages about 2 years ago, which at that time provided the largest coverage of Indian languages. It covered 16 Indian languages plus English, so total of 17. And both kind of native, and in particular, we paid a lot of attention to transliterated text. And we made this model available for free on Hugging Face and TensorFlow. And we saw that, again, for a variety of benchmarks, like name entity recognition, part of speech, this is question answering, it could do a pretty good job and improve the accuracy of the underlying model for many of these tasks. So we launched then a new version of Google Assistant product, which was supporting 8 Indian languages. So we launched a new version that was using Mural to understand the user intent. And now, when the user, let's say, talked about setting an alarm in different languages like Marathi, and these are examples from Marathi, Bengali, Gujarati, and their English translation, that they are speaking in a very conversational style. Look, wake me up at 4 in the morning, set an alarm, and make sure you don't forget. They're telling the mobile phone, giving those instructions. So from this instruction from the user, can you generate a call to create an alarm with the using that appropriate API? So this is the part that, again, our neural semantic parser is able to do for all of those 8 Indian languages. And we saw that there was a significant improvement in the accuracy of being able to recognize those commands. So then we decided to raise our ambitions further. The initial thought was, hey, instead of 16 Indian languages, let's support 22, all of the 22 scheduled languages. But then my colleague Partha Talukdar, who leads that work, he said, no, let's aim bigger. Let's make sure that, so he looked at, again, the coverage of, again, number of speakers for different Indian languages, and we saw that there are 60 Indian languages which have at least 1 million speakers. And there are actually 125 Indian languages that have at least 1 lakh speakers. So we decided to make sure that if a language is spoken by at least 1 lakh people in India, we want that covered by our models. So that led to this concept for, again, this target for 125 languages to be covered by a single model, which is being built by our team. We call it Morni. It sounds simple that, oh, cover 125 languages, but it's actually very, very, it's a complex problem. So in particular, out of these 125 languages, 72 are what we call zero corpus languages. Zero corpus means there is zero known digital data on any of those 72 languages. So despite India being linguistically such a diverse country, it always amazes me how little digital content we have for many of our languages. So that led to, again, some innovative work. Can we get started with just lexicons, the dictionaries that we have for those zero corpus languages? So we started jump-starting things from that. We started looking at, can we mine YouTube videos for those languages? And before we mined YouTube, one of the things we had to do was recognize what language, because chances are people from that region are already uploading videos on YouTube, but YouTube today only gives you a choice of some, I think, 56 languages when you upload a video. So we expanded that to over 500 languages, and then we built a specific classifier that, given a video, would try to recognize what language that video is in primarily. And we improved the accuracy of those classifiers. And then we also launched this project called Vani in collaboration with the Indian Institute of Science, where we said there is, to truly capture the linguist diversity of India, we really need to collect speech data from every part of India. There's a saying in India, kos kos pe badle pani, char kos par vani, which means every 4 kos is, I'm not sure exactly what's the exact length that one kos, but every 4 kos, there is a change in language. We are doing that data collection together with our partner in stages. We have already completed phase 1, where we have collected close to 5,000 hours of data from 80 districts, and we have made all of that data available in open source to any developer, so to any practitioner, any startup that wants to build its own speech model, and academic researchers. And over the period of the next few years, our goal is to collect data from each and every one of the close to 773 districts in India, so that we capture that full diversity. And what we do is, we don't ask people to speak in a given language. We just describe an image, a locally relevant image, and we say, describe in any language that you feel comfortable talking in. And then just tell us what that language is. And because of this, not being anchored on language, we've been able to get many kind of relatively low representation languages featuring in these videos. So it's been very fascinating. Oops. So the other thing now we are doing is to, again, compose these capabilities, the strong Indian language representation capabilities, with the powerful reasoning capabilities of our large language model. Like ULM is the most powerful model internally available within Google, called Unified Language Model, externally known as PaLM-2. And so we've been now looking at ways in which we compose all of these powerful reasoning capabilities with the strong Indian language capabilities of models like Morni, and then bring the best of both. Just very briefly, in areas like healthcare, before you start applying AI to health, first the health data needs to be in digital form. And we all know that in India, when you go to a doctor, let's say a local clinic, usually all of that health data is sitting not in an electronic form, but in a paper-based prescription. So we started working on this problem of, given that medical prescription, is there a way you could actually digitize this? And again, it's a very challenging task. We do have products like Google Lens. However, when we looked at the accuracy of our own products in being able to, let's say, given a prescription, even infer the medicine names correctly, we saw that the accuracy was quite low when we got started, of the order of 10 to 11%. So we've been basically applying ideas, combining vision with large language models to look at how they work together to appropriately segment this and recognize some of these words. So the simple version of the idea is that, look, if this is a medicine name, this has to come from one of the vocabulary, right, or one of the known medicine names. But we do some things even more sophisticated. Let's say somebody has written paracetamol, and the doctor's handwriting is almost as bad. A typical doctor's handwriting is almost as bad as my handwriting, because I used to have a conjecture that I have the worst handwriting of the entire universe of literate people. My teacher used to find it very hard to understand what I've written, that, look, your E looks like a C. So let's say if the doctor's E looks like a C in the paracetamol, and you've recognized the word based on the signal from the large language model, oh, the word is paracetamol. Now you can go back and provide a signal to your vision model that, look, this really is an E, and therefore when you see similar deformed characters, you can recognize those as E's. So essentially, we are using these combination of vision and language model techniques to improve the accuracy on tasks like this. And finally, agriculture, which has been a relatively untouched area by technology. So to tackle these problems at large scale, one of the things we started building, and if I had more time and ability to kind of have that laptop right here, I would have shown you a demo. In fact, if you click, I don't know if you can you click on that demo? And I would love to show the system that we have built, which kind of, from satellite imagery, it allows you to zoom in. It's an overlay on top of basically the Google Earth engine, and it lets you, it lets you see all of the different boundaries of farms based on usage patterns, lets you see various sources of water, let's say the pond or a well and so on. And we are currently working also on building models to recognize the crop which is being grown. Because once you make all of this information available in a scalable manner for a given region, now to a bank, for instance, now it gets much easier. Let's say when a farmer applies for a loan, instead of having to send an agent 50 kilometers away to the field, the bank can, at their fingertips, kind of infer the crop that is being grown. They can look at the history, and they can estimate the income the farmer is going to have at harvest time, and then go and approve that loan. Or if the farmer comes looking for, let's say, insurance for cotton crop, they can actually validate if the farmer is indeed growing cotton. So this way you can enable a lot of these scenarios today which keep the farmers out of the formal financial sector, and even do things like, in a few months, right, this part of India, again, will be dealing with the problem of stubble burning. So can you incentivize farmers to basically not burn stubble, directly transfer money using all of that Jan Dhan accounts and UPI and all of the wonderful public digital infrastructure, transfer that money into their account, but hold them to their pledge of not burning the stubble. Now you can actually monitor that through satellite imagery, whether the farmer is actually indeed honoring that pledge in return for the money that you transfer to them. As well as you can, in fact, if you are able to credibly model the carbon content of the soil, there are regenerative farming practices and so on, which lead to greater carbon holding potential of soil, and you can then start to incentivize farmers even financially through carbon credits if you are able to model this carbon content, which today is possible only through very expensive lab tests, and we are trying to see how satellite imagery can help make a difference. So with that, let me conclude that AI is already here and impacting every industry and the world at large. We have seen, again, this very exciting rise of foundation models, which are these models, in particular large language models, but increasingly they're going to have all of these multimodal capabilities. They will also understand images, speech, as well as videos, trained on large data, usually with self-supervision. And as we build all of these large language models, there's also a huge need and an opportunity to develop them in a manner that brings benefits to billions of new people in countries like India. And again, it leads to very, very interesting challenges, but this is what makes it very, very interesting to be a researcher or a practitioner today for AI, because you can really see the real world impact of your work and really help improve the lives of billions of people. So with that, let me stop here and thank you.
Thank you so much, Manish. And can we please request Ritika Basu, Head of Technology, Mercer India and Mercer Marsh Benefits, to come on stage and felicitate Manish Gupta. Thank you, Ritika. Thank you, Manish.